So for the last chapter that we're going to cover this year, we're going to talk about electrochemistry. And electrochemistry is going to harken back to redox reactions and other types of like single displacement reactions, for example. We're going to take a look at the actual movement of electrons through these systems. Okay, we'll start by talking about a galvanic cell. A galvanic cell is a device or a setup that changes chemical energy into electrical energy. Okay, it's essentially using a redox reaction. You have the reducing agent, which reducing means to gain electrons, right? The reducing agent is the thing that actually is oxidized, so it loses electrons. It transfers electrons to the oxidizing agent, which gains them and is reduced. Remember that oxidation is loss of electrons, oxidation state becomes more positive, and reduction is the opposite of that. Okay? So what's different about a galvanic cell is that we do this redox reaction. Instead of doing it in one beaker, we separate the half reactions into two beakers, and we connect them by a wire. So here we have permanganate in an acidic situation on one side, and on the other side we have some iron 2 ions. Now nothing will happen because the electrons can't flow to complete the circuit unless I connect those two beakers in a certain way. Okay? If I put them in the same container, the electron exchange occurs directly, and I can't use the exchange of electrons to do anything. The work is released as heat. It might heat up a little bit. Okay, so to use the energy that's released, we keep the half reactions separate, and the electron transfer will go through a wire. We use a salt bridge or a porous disc, something that will allow unrelated or counter ions or spectator ions to move back and forth to balance the charge. Okay, and when we connect it like that, now we have a way for electrons to flow. So this is a galvanic cell, and the E minus, of course, is electrons, and you'll notice that they are moving from essentially the left container to the right container through the wire. We have a porous disc, and I've labeled these for you, the beakers on the left. The beaker on the left is labeled the anode. That's where the reducing agent is, where oxidation is going to be found, and then the other beaker is called the cathode, and that's where the oxidizing agent is going to be found, and the oxidizing agent is itself reduced, so reduction happens over there. Electrons flow from the reducing agent to the oxidizing agent. Okay, electrons flow in the direction of the transfer. Okay. Now, the locations of each half reaction are found in the anode. The oxidation happens in the anode. Notice it says reducing agent in the diagram, but over here I say that the oxidation is happening. Remember, the reducing agent is itself oxidized, okay? And the cathode, the oxidizing agent, is itself reduced. Easiest way to remember this, I think, is with the mnemonic red cat. Reduction happens at the cathode. So if you're looking at a galvanic cell and you want to figure out which direction the electrons are moving, just remember a red cat and it should help. Okay. Now we can quantify this a little bit. We have something called cell potential, which is represented by this E cell. And that's E is related to the electromotive force. Okay. It's essentially a driving force on the electrons to move them through the wire. The more the force is, the more electrons you'll be able to move, or the faster they'll be able to move. Okay, so it's called the electromotive force, EMF. The units of E cell are volts, named after Volta, who came up with this concept. A volt is a joule per coulomb of charge. Now we'll talk about what coulombs are in just a minute. Okay. Don't worry too much about 17.1 at the end. There's a lot of physics in there. If you've taken physics and you want to take a look at it, go for it, but we're not going to really need to know that. Okay. So let's take a look at how we get E cell. We need something called standard reduction potentials. Each half reaction gets a value of a number of volts involved in that half reaction. The total E cell, the total cell potential of a galvanic cell, is the sum of the individual potentials for the half reactions. Okay. Now, when you look up reduction potentials, because they're called reduction potentials, they'll always be written as reductions. But remember that in a galvanic cell, in any redox reaction, you not only have one reduction, but you also have an oxidation. So you're going to have to switch one of them around, flip it around, and change the sign. Okay, so when you reverse a half reaction direction, you change the sign of the reduction potential. Okay. If you balance the equation and you use coefficients, you don't have to multiply the reduction potential by anything. You just use the value. It doesn't matter the concentration. Okay, it's an intensive property. So this is taken from your book. You will see this on the exam with the supplementary materials. These are some of the most common half reactions that we'll use all the time, and their standard reduction potentials. Remember, you'll have two half reactions in a full galvanic cell. In a full reaction, one of them will have to be flipped to oxidation, and that means you'll have to change the sign of the other one. These are E standard cell potentials, standard reduction potentials, which means that we're talking about standard conditions, which means the solutions are 1 molar and gases are 1 atmosphere, and the temperature is 298 Kelvin. That's standard conditions. Okay. All of those numbers in that table were determined experimentally by referencing something called the standard hydrogen electrode. Okay. The standard hydrogen electrode is platinum electrode in contact with 1 molar acid concentration and a 1 atmosphere pressure of hydrogen gas. And it was assigned arbitrarily and a reduction potential of 0. And so we can calculate all of the other reduction potentials by pairing that one up with any other half reaction and measuring the total E cell. Okay? So this is what it would look like. The standard hydrogen electrode is essentially an inverted tube with a side arm so that you can flow gas into it. And then that tube is inverted with a platinum electrode into a solution that contains an acid at a concentration of 1 molar. That's how you make it. It's a little bit labor intensive because you need a canister of hydrogen to provide 1 atmosphere pressure of hydrogen. The platinum electrodes are not cheap, but once you set it up in the other beaker, you can use any half reaction and then measure the voltage of the cell. And since we've assigned the platinum electrode to have a standard reduction potential of 0, and E cell is the sum of the two potentials, then we just know the other one. We'll know the oxidative potential on the other side. Okay. Notice on this one, the anode, I've got my zinc 2 plus ions and sulfate ions. So I've got a solution of 1 molar zinc sulfate. And the electrode that I've chosen is made out of zinc metal. I can do that. I can use the metal that is in my solution as long as the reduction produces that metal when it's reduced. So when zinc is reduced, when it loses its electrons, when it gains electrons, when it's reduced, it will become zinc metal. And when zinc metal is oxidized, it will become zinc plus 2. So because that's my half reaction, Zn goes to Zn plus 2 electrons, I can use a zinc metal electrode. If I'm doing something and I don't either start with a metal or end with a metal, then I'm going to just use platinum as my electrode, because platinum is fairly unreactive and it conducts electricity really well. Okay, so if your half reaction includes a solid metal as part of your half reaction, then make your electrode in that half reaction cell. Make your electrode out of that metal. In this case, zinc is part of my half reaction, so I'm going to make zinc my electrode. Okay, so here's an example. We're going to find E cell for this following reaction. We have iron 3 ions and copper reacting to form copper ions and iron 2 ions. Okay, so the half reactions are going to be Fe3 plus an electron to Fe2. Okay, Fe3 down to Fe2, that's reduction, so I just look up the reduction potential for that change, and it's 0.77 volts. The other half reaction, I'm going to have to switch, because what's happening in the overall reaction is that copper metal is actually losing electrons to become copper 2 ion. But the way I'd look it up on the table, it would say copper 2 ion gaining electrons, reduction, to form copper metal. So I'm going to have to switch that one around. And when I do, I change the sign to negative 0.34. E cell for this is just the sum of my two E values, my two standard reduction potentials. So 0.77 minus 0.34 is 0.43 volts. That's E cell. Okay. I can, instead of drawing the beakers out and labeling and everything, I can do that, but I can also write what's called line notation, which is a very short way of writing, describing a whole cell. Okay. We always put the anode on the left and the cathode on the right. We separate the anode and cathode information with a double vertical line. We separate phases in a half reaction. So if you have a solid metal in a solution, for example, we separate those two phases with a single vertical line. Okay? If no part of the half reaction is solid, in other words, there's no solid metal involved, then you use the platinum electrode. Otherwise, use the metal. The electrodes are on the opposite ends, the far ends of the notation. So whatever your electrode is made out of, that's the first thing you write for the anode, and it's the last thing you write in your line notation for the cathode. Okay? So here's an example of line notation. It looks strange, but let's explain what's going on here. What does this tell me? If I'm reading from left to right, it tells me that I have a magnesium electrode. My electrode is made out of magnesium metal, and it's sitting in a solution of magnesium ions, maybe magnesium nitrate, for example. That's one half reaction. That's my anode. So what happens at the anode? Oxidation happens at the anode. The magnesium metal on the electrode is going to lose electrons to form magnesium ion in solution. Then I have the double line which separates the two. Think of that as maybe like the salt bridge. And on the other side, I have a solution of aluminum ions separated by from an aluminum electrode, solid metal aluminum electrode stuck in that aluminum ion solution. Well, that's the cathode, and reduction happens at the cathode, red cat. And so reduction is going to be aluminum 3 plus gaining electrons to become solid aluminum metal. And that solid aluminum metal is going to stick to the piece of aluminum that's already sitting in my solution, the aluminum electrode. So what's happening here is the magnesium, solid piece of magnesium that's acting as my electrode on the anode is going to be getting smaller because magnesium atoms are going to be losing electrons and becoming magnesium ions, which are soluble. And then on the other side, I have a piece of aluminum metal stuck in a solution of aluminum ions, and as the electrons flow, my aluminum ions are going to be gaining those electrons and becoming solid aluminum and sticking onto the aluminum electrode, and the aluminum electrode on that side is going to be getting bigger. It's going to be getting more mass. Okay, here's another one. Now in this one, I have a platinum electrode stuck into a solution that's a mixture of chlorate and perchlorate ions. Why is it a platinum electrode? Because the half reaction from chlorate to perchlorate does not involve anything solid that I could use as an electrode, so I use platinum. Double line is my salt bridge, and over on the other side I have permanganate and manganese 2 in solution. Neither one of those is solid, so I have a platinum electrode on that side. Okay? So once I know the E cell for the reaction, galvanic cells will always run in the direction where E cell is positive. So if you do your E cell calculation, it comes out negative. That doesn't mean that it's not going to work. It just means that it's backwards. It means that the reaction will run the other way. The cell will be the other. So you'll switch your anode and cathode. You'll switch your oxidation and reduction to have reactions. To describe a galvanic cell, you want the balanced chemical equation for the reaction and make sure that you write it in such a way that you get a positive value for E cell. You want to give the direction of electron flow. Okay, remember electrons always flow from anode to cathode. Okay. And you want to assign the anode and cathode, and then maybe give your line notation. So they may tell you a little bit about the cell and ask you to do all of these things on the national exam. Okay, so here's an example. Describe the galvanic cell based on the following half reactions. We have silver ions becoming silver metal. There's your reduction potential for that, and we have iron 3 going to iron 2. There's your reduction potential. So let's describe this reaction. The first thing I need to do is figure out which of these I have to reverse, right? One of them has to be an oxidation. I'm going to reverse the one that will give me a positive E cell, right? So I know I have to reverse the Fe3 plus to Fe2 plus because if I reverse the other one, I'll have a negative value when I add those two together. So if I reverse the first one, I'll still have a positive value. So the iron equation must be, instead of Fe3 plus electron to Fe2 plus, it must be the other way around. Okay, so I put them into my new equation. It means silver ions and iron 2 ions are reacting to produce silver metal and iron 3. My E cell is the sum of them. It's just 0.03 volts. It's not a lot of force there, not a lot of work I can do with this, but there it is. Okay. Now the direction of electron flow will always be right in the direction from oxidation, which loses the electrons, to reduction, which gains them. Okay, so the iron is being oxidized, the silver is being reduced, so the electrons flow from the compartment that contains the iron 2 ion to the compartment that contains the silver ion. And that means that the anode and cathode are, the anode is where the oxidation happens, and the cathode is where the reduction happens, red cat, remember? Okay, so this is what it would look like. Now, why do I use a platinum electrode in the anode? because neither part of that half reaction is a solid. But over on the other side, the cathode, part of my half reaction is solid silver. So I can use a silver metal electrode. That'd be a little expensive, but I can do it. Okay? Porous disc to allow the non-related ions to travel to balance the charge, and the electrons will travel from the iron 2, iron 3 side to the silver side, from the anode to the cathode. Line notation would look like this. Okay? And that's how you describe a galvanic cell.